Welcome to Chapter 18, the first chapter in the next unit, Unit 5, and we're talking here about sampling distributions. So first of all, we're going to talk about what exactly is a sample proportion, because this first part is talking about sample proportions. To get a sample proportion, we're going to collect some sort of random sample of a size n, maybe by an SRS, so a simple random sampling. And then we count how many have a particular characteristic that we are interested in. So the word characteristic there should clue you in to we are going to talk about sampling proportions with categorical variables because it has a characteristic. Okay, so p hat, and for some reason this rectangle is what shows up. It doesn't show up this way on the other PowerPoint, but this is a hat, and think back to previously, the hat was our approximated value or our observed value. Okay, so p hat is the proportion of people that are of interest to us in what we saw in our sample. Okay, so how we model it. So we can look at a sample of a size 1,000 and we know the results of that particular group. And we can create a histogram, and we're going to do that a little bit later with an example. But what about other random samples? Well, we don't know what they look like. So how can we possibly make any conclusions about what the other ones look like? What would a histogram of all of the sample proportions look like? So if we took all of the sample proportions together and put it together, what would it actually look like? I realized I haven't answered any questions. Well, going from that smaller set, now we want to look, well, what is the true proportion? So P, this is what our actual value is. So P is the true proportion from the entire population. If we were able to poll every single person who lives in the United States or lives in a particular state, and we ask them our question about whatever characteristic that we're looking for, P is that true proportion. But unfortunately, we never know what really that is. There could be people who are not there that day or don't participate in our survey. Okay, so we need to always remember out there somewhere is what that proportion is. So in this book, we talk a lot. Well, we talk about think, show, and tell. So now we're going to talk a little bit about imagination, that you have to imagine that we can poll every single person in our organization. Okay? All right, so sample proportion, that true proportion. If we took all of our samples together of the same size, we will see different sample proportions. But none of them are going to be exactly the same because everything varies. So if in the state of California, we pulled people from one group, 1,000 people, people from another group, 1,000 people, and we're all looking for the same characteristics, they are going to vary. All of our samples are going to vary, but they all came from the same set. We're looking at all of the females between the ages of 20 and 35. So if we pull one group of females between 20 and 35, we're going to get one proportion. If we pull another, we're going to get another proportion. Okay, but they all come from the same exact set. Remember that this sample proportion is really p hat. So when you see that little rectangle, make sure you're writing it down as a p hat. Okay. All right, so let's look at a couple of examples. Where is this all fitting in? So in a previous election, Obama got 56% of the vote. So of the people who voted, 56% of those people voted for him. So that's a true proportion because we have all of those people who voted. But before the election, let's say that I took a whole bunch of samples of size of 1,000 people, and these are my sample proportions: 55%, 52.6%, 57.1%. So they're all varying because they're different groups. Okay. If I put it together in a histogram, the histogram would look something like this. Here are the numbers of samples. If I have the percentages down here, 200% of the samples fit right in here, 100% of the samples fit in here, etc. So this should look very familiar to you. It looks like a normal curve. So if we took all of our sample proportions and put them together in a histogram, we get a normal curve. Well, why does that work out? Okay, so all of my sample proportions center around that true proportion. The true proportion P is what is the mean in this case. Okay, It's the probability, that's why it's still okay to use a small letter p here. It's the probability that, that the people would vote that way. Okay, very few will go real low, very few are high. Okay, so if I look at this, very few are high, very few are low. Most of them center right around the mean. Okay, so the sample proportions would vary. So how do we figure out the standard deviation of that? Well, we have a formula for that. Okay, so we have two parameters, and because we're talking about the population, that's why we have these parameters. Remember, population, parameter, sample is statistic. So we have our mean and standard deviation. Here's more formulas to add to your already growing list of formulas. Okay, so we put the true proportion in the middle of the normal model as the mean because that's our expected value. So that's the small p, that is where our center is. Okay, so with proportions, these are our standard deviations. So the standard deviation of the sample population, or not the sample that we're looking at, the sample proportion, that's what I meant, is the p hat. Okay, and then we simplify this. So the square root of NPQ, that should look familiar because we just did this with binomial distributions. But now because we want a proportion, we're going to divide it by n because n is our large group of people, or in our sample that we have. Okay. And then when I do my simplification, so the n's will cancel, I'm left with still a square root in the denominator. So I can go into more detail, but this formula needs to be written in your notes. Okay, so we're talking about the population. Okay, we're talking about the p hat, and we're talking about the proportion. So that's what goes in here, the sample proportion. Okay, so make sure that's in your notes, the standard deviation. Okay, so here's our normal model picture. P is the mean, that goes right in the center. And then we have 1 standard deviation, 2 standard deviations, 3 standard deviations away. That is nothing different, but we're going to calculate the standard deviation a little bit differently because we know that we're talking about the proportion instead. Okay, so if we go back to the President Obama example, so P, which is our mean, our expected value is 0.56. We expect that 56% of the people are going to vote for him. That's where our mean is. And then we calculate the standard deviation. So here's P times the 0.44 divided by N, which is the 1,000 people that we talked about. The 0.44 is Q. So here's P and Q. And remember that Q is 1 minus P. Okay, so the standard deviation is 1.58. Okay, so 68% of the samples will be off by 1.58. Where did the 68 come from? Because 1 standard deviation on either side of the mean, here's where 68% of our people should be in there. Okay, so we have 56.56 is the mean, and then 1 standard deviation in either direction. Okay, all right. Okay, the next thing we have to talk about is sampling error. Okay, so the standard deviation is really what the sampling error is. It's not really an error, although that's what they call it. It's really just how much the values are going to vary. Okay, so a better term would be sampling variability. So that is an important thing to note, that sampling error is the standard deviation. It's how much off the center the data will be. So sampling error and sampling variability are the same thing. Okay, so a recap of this section. So if we draw repeated random samples of the same size from some population and we measure the proportion, so p hat, that we get for each sample, the collection of the samples will pile up around the underlying population proportion in such a way that it reflects the normal model. So we have the center and we have these different samples we've collected data from that we're looking for a particular characteristic. So by taking a variety of random samples, we know that it's going to center around the mean. Okay, so there are a couple of assumptions that we have to make. So the sampled value must be independent of each other, and n has to be large enough. Okay, so let's talk more about that in terms of conditions. So when you decide that you're going to be able to use a normal model with this, you need to show these 3 conditions. Okay, so you'll want to make a list of these, and then that's the expectation that you show, there's lots of showing in statistics, that you show that you have all of this information. Okay, so when we have our proportions, okay, we want to show that randomized condition, so that some sort of randomized sample was used to be able to collect the data. The 10% condition, so the sample size n must be no larger than 10%, okay, and that is assuring independence. So no larger than 10% of the whole population. We can't use any more than that. And this came up with the binomial distribution last chapter, that we have to expect at least 10 successes and 10 failures. So n times p has to be greater than or equal to 10, and n times q has to be greater than or equal to 10. Okay. All right. So here are your 2, just in case you didn't write them down yet. Here are the 2 formulas that you need to know here. Okay, so a proportion isn't something we just compute from the data. We see it as a random variable with a distribution. So mu of p hat is equal to p. So the mean of this parameter is equal to the population mean. Okay, and then here we can calculate the standard deviation of that as well. Okay, so let's go through an example. All right, so suppose 13% of the population is left-handed. A 200-seat school auditorium has been built with 15 lefty seats. I don't know if you know what those are, but in high schools or in colleges, they often have these desks with half of a table in front, or so like half the desk. And they make them usually for right-handed people. They have this piece on the right-hand side, but for lefty seats, it's on the left-hand side to make it easier for the left-handed persons. So that's what that is, okay? So in a class of 90 students, what is the probability that there will not be enough seats for the left-handed students? Okay, so information that you need to write down. 13% of the population is left-handed, 200 seats in the school, and we have 15 lefty seats, and we have 90 people. So the probability that there will not be enough seats. Okay, all right, so let's put some information on that. So I want to know, wrote it in a little bit different way. I want to know what's the probability in the group of 90 students that more than 15 will be left-handed. Okay, because that's what the question is asking. There won't be enough seats. So let's find out what's the percentage there. So 15 out of 90 is 16.7%. And I need the probability of finding more than 16.7% left-handed students out of my 90 if the proportion of lefties is 13%. Okay, so the 16.7 came from I want to find the probability that more than 15 will be left-handed in the group. Okay, all right, so independence, is that met? Is it, do I have less than, is one independent from the other? Well, yes, it is. Okay, so I don't need to worry about that. So being left-handed is independent of that, and so that not an issue there. All right, so as far as my conditions go, randomized. Is it a randomized sample? Well, sure it is. Of the students at the college or at the high school, it's just people who are taking that class, so it is a randomized set. Okay, are there less than 10% of the population? We don't know how big the school is, but we're going to assume that it's less than 10%. A group of 90 students, if they're going to have an auditorium that's going to be big and a class of 90 students, I'm going to say that it's probably safe to assume that it's going to be larger than that. Okay, and then here's my success or failure. So my success is 11, which is greater than 10, and my failure is 78, which is greater than 10. Okay, so we're going to calculate the standard deviation of p hat using this formula. So when I find that out, the square root of pq over n. So right down here is where that has been calculated. So it equals 0.035. So I have my p, so the square root of p is 0.13. Times 0.87 and I'm going to divide it by 90 because that's how many people I'm talking about. Okay, so when you do that calculation, we get 0.035. Okay, all right, the next thing I had to do is find the z-score because I want to know percentage-wise. I need the probability of finding more than 16.7% left-handed students. So I find the z-score. So down here, I'm looking for the z-score. So I have p hat. That's my p hat is what I'm. That's yeah. Okay. So I have p hat, and I'm subtracting the mean from that. So 0.167 is what that approximated mean is. That's my the percent up here. The 15 out of 90 people. Okay, so 0.167. That's my smaller population. And then 0.13 is the mean of all of the people because 13% of all people are left-handed. And then I divide it by the standard deviation to get a mean of z-score, of 1.06. Okay, so this in notation, we need to start paying attention to notation a little bit more. Okay, so I want the probability that p hat is going to be greater than 0.167. So I translated that into a z-score. I want the probability that my z-score, my z, is going to be greater than 1.06. So you get out your calculator, plug in this z-score, and the answer is 0.1446. Okay. So then what's my conclusion with that? What's my conclusion that does that work? Does that work okay? Okay, so what I say is there is a 14.5% chance that there will not be enough seats for the left-handed students in the class, because the question was just asking that. I need the probability of finding more than 16.7 left-handed students out of a sample of 90 if the proportion of lefties is 13%. Well, it's 14.5% chance that there will not be enough lefty seats. That's why it's shaded in this direction. Okay. All right. So what we just got done talking about was the categorical variables. So now we're going to talk about, well, for quantitative variables, what do we do? What do we do with that? Okay. So this is chapter 18, part 2. So the mean or average of a sample is the average of a sample. Okay. So y bar or x bar. So a sample's average height. A sample's average weight, the IQ. Okay, so we're looking for an average, but a number this time because now we're talking about quantitative variables. So much of this is similar to what we just got done talking about. So we never know the true average length of a pickle, for example. If we look at a histogram of lots of different sample means, they will be centered around the true sample mean. This is just like the first part of this. Okay, so the distribution of sample means still fit the normal model. So the sampling distribution of any mean becomes more clearly normal as the sample size grows. We don't even care what the shape of the population distribution looks like. That's just what we know is going to happen. So the central limit theorem is going to seem like it's really obvious, but this is a huge deal when we're talking about statistics and inferring, which we're going to be getting to over the next few chapters. So the mean of a random sample has a sampling distribution whose shape can be approximated by a normal model. The larger the sample, the better the approximation will be. Okay, so the larger sample that we take, the better the approximation is. And that's what is central to, yes, called the central limit theorem. Okay, so we look at the mean of a random sample, and we say that the mean of the random sample has a sampling distribution whose shape can be approximated by a normal model. So we are going to be going back into z-scores and normal model because now we're looking at these different either the proportion, the sampling proportion, or with these sample means. Okay, so the larger the sample, the better the approximation. So here are the conditions. So very similar to what we just got done talking about. They have to be randomized. We have to show that there's independence between the variables here. Okay, the 10% condition, the sample size n can be no more than 10% of the population. And it has to be large enough. So again, it's going to depend on the information that we're given and the situation of whatever it is we're collecting data. Okay, so standard deviations and means, it's very similar. So the means or the averages have smaller standard deviations than individual values. The size of the sample affects the standard deviation. The bigger the sample, the less the variation. Okay, so this goes back to the central limit theorem. Okay, the bigger the sample, the less the variation. So towards the end of the year, you will be designing an experiment. And this is important to keep in mind, that the bigger the sample we take, the less of the variation. Okay, so this symbol is the true standard deviation of the population. To find the standard deviation of this sample mean, we take the standard deviation of the whole population divided by the square root of whatever n is, how much is in our data. Okay, so this is an important slide. Okay, again, this is the hat. So sample versus truth. So we have the sample versus the truth in the population. So this side, the proportions, we're talking categorical variables. And on this side, we're talking the mean with quantitative variables. We're talking quantitative variables. Okay, so the sample proportion, and without the hat is the population proportion. The sample standard deviation, so the standard deviation with p hat is this. And the population standard deviation, it will be the same. When we're talking with quantitative variables, here is our sample mean, the population mean, the sample standard deviation, and then the standard deviation of the population. Okay. All right, so one big problem. Okay, so in order to be able to find the standard deviation, we have to be able to figure out what the true standard deviation is, all right, what the true proportion is. But of course, we can never be able to figure that out. Okay, there's no way. It's impossible to actually be able to figure out every piece of data in an entire population. So this is called standard error. So remember we talked before about it was variability. Okay, so here's how we find the standard error. So the standard error is really the standard deviation. Okay, so I'll give you a few minutes to write this down. Okay. So let's do another example. It's the last example. So suppose the mean adult weight is 190 pounds with a standard deviation of 59 pounds. An elevator has a weight limit of 10 people or 2,500 pounds. So what is the probability that 10 people who get on an elevator overload the weight limit? So information that you need to write down, the mean. So X bar is 190, or mu is 190 because it's the population. And the standard deviation is 59 pounds. This is for the whole population. This is somebody else have given us this information already. So an elevator has the weight limit. Okay, all right, so here's really what the question is. Really what we're asking is the probability that their mean weight is greater than 250 pounds. Because if we have 2,500 pounds is the weight limit for the elevator and we have 10 people who get on, what's the probability that each person's average weight is 250 pounds? Okay, so we go through independence, randomization, 10% large enough. Okay, we have all of that. Okay, mu is 190 and the standard deviation is 59. We figured out what the standard deviation here is. We were given that the standard deviation is 59. We have 10 people. So when we calculate that, we get 18.66. Okay. All right. So same process. We're going to use the normal model, figure out the z-score. So 250 minus 190 over the standard deviation is going to give us 3.21. So what is the probability that the average of the group, or the average person getting on the elevator, is going to be greater than 250 pounds? And then we figure out the probability with the z-score. Okay, so let's get in the habit of writing this notation. So Z is greater than 3.2. I'll use it with the calculator. Right here is that value. Okay, so then what's our conclusion? The chance that a random collection of 10 men, this says men, I didn't put that in here, okay, of the 10 men will exceed the elevator's weight limit is only 0.0007. Okay, so if they are a random sample, it's quite unlikely that 10 people will exceed the total weight allowed on the elevator because we're all the way down in this teeny tiny little tail. Okay, all right, lots of information. Please make sure you have the formulas written down, and that's it. Bye.